Hi everyone. So in this video we are going to discuss IP header. So let me move to the next slide. This is the structure of IP header as you can see. So here there are 32 bits. Like if you see, this is bit number 0 and this is 31. So this length is telling us that this is 32 bit long, and each row is having some specification. So if you look at the first row, then it is saying that version is having 4 bits, and header length, this HLEN means header length, it is having 4 bits, and there are some other fields like service type, this is having 8 bits. So the number is written over here, and the whole completely one row is consisting of 32 bits, right, which means 4 bytes. So this means 4 bytes, again 4 bytes, again 4 bytes, again 4 bytes, again 4 bytes. So as you can see, there are total 20 bytes which are fixed. Now there are some options or padding, like it also includes padding. So these are consisting from 0 to 40 bytes. So if you see this notation, I mean this is just to show that it is a variable, which means it may have 0 bytes or it may have up to 40 bytes. So if I ask you that what is the size of IP header, then you will say minimum is 20 bytes, because these fields are fixed. So minimum is 20 bytes, and the maximum is 20 plus 40, which is 60 bytes. Right? So this is the minimum size of IP header, this is the maximum size of IP header. Generally we do not use options, but they are there for some of the services, but generally like most of the IP header does not use options. So generally the size of IP header is 20 bytes only, but it can range till 60 bytes. Now let's talk about every field one by one. So first field is VER, which means version. Now version is having 4 bits, which means there could be from 0000 to 11111. There could be these many versions. And out of all these versions, only 2 versions got success, which is IPv4 and like V4 version 4, and another one is version 6. So like many of the after IPv6 there is no version that got published. So in between IPv4 and IPv6 there might be some version which is V5, but it was not successful, so they have not published it. Now we have only 2 versions which are successfully implemented, IPv4 and IPv6. In our syllabus we only have IPv4, so that is why like we will be only studying IPv4. Like earlier IPv6 was also in the syllabus, but it got removed now. So basically like to start with the GATE syllabus was only having IPv4, and then for 2-3 years they included IPv6, then again they removed it. Okay, so we will be only studying IPv4, and this header is for IPv4 header. This is for IPv4 header, which means this version will always be, in our case this always be 0100. This will be having these 4 bits, which means this is version 4. Now another field is header length. As you can see, the header length can go from 20 bytes to 60 bytes, right? And this is having 4 bits only, which means I can represent from 0 to 15 over here only, because since this is having only 4 bits, which means it can range till 4 ones, which means 15. 4 ones is just 15, but my header length can go from 20 bytes to 60 bytes. So you got the issue, right? My IP header length, as we have just seen, it can range from 20 bytes to 60 bytes, but my header length field is just saying that I can represent from 0 to 15. So obviously 0, I will never be having 0 in my header length, because the minimum header length is 20, but anyway it is allowing me to represent from 0 to 15, but my actual header length is 20 to 60 bytes. So what I will do, I will do one thing, that I will scale my actual header length and I will divide by 4 to my actual header length, which means if my header length is 20, then in my header length field I will be just writing 5, and if my header length is 60, then in my header length field I will be just writing 15. Okay, so it will solve this problem, which means suppose my header length is 20, then I will be having this as my header length field, right? So I will be having 0101. Why? Because 0101 is for 5. See this? This is 2 power 0, this is 2 power 1, this is 2 power 2. So it will be 5, right? So that is why if my header length is only containing 20 bytes, so I will be having 0101 in my header length field. So if I ask you that what will be the initial uh, 2 bytes, or sorry, initial 1 byte, right? Initial 1 byte of my IP header. Then initial 4 bits are just IP version, which is 4, which means 0100. And then suppose my header length is having 20 bytes, then I will be having 0101 as my header length. So this is for my version, and this is for header length. So this will be my initial byte of my IP header. I hope you got it. So why I am having 0101 even though my IP header is 20 bytes, it is just telling me 5 bytes because I have scaled it. So whenever receiver received it, it will not treat it as a 5, it will treat it as a 5 into or something into, like whatever is this binary number, 2 decimal into 4, and then it will be treated as 20 bytes, right? So this is about the first two fields. Now what about this service type? So there is another field that is service type. Now they also call it type of service, and then it got some name change, which is the service code pointer, something like that. It got redefined after some time. So anyway, this field is not used much, so we will be not studying it. So like these are hardly ever used, so we will not be studying this service type. Now the next field is total length. So version is done, header length is done, service type of service is done. Now next field is total length. Total length means what? Total length including the header length. So this total length means like header plus data. Header plus data. Now it is having 16 bits, which means what? You may have 16 ones, from 16 zeros to 16 ones. And obviously you cannot have 0 as a total length because minimum header length itself is 20 bytes. So you cannot have this as a 0. But anyway, this is allowing me to 0 to this 16 ones means 2 power 16 minus 1, which is basically 653 or 65535, I think 535. So this field can contain 65535 as a value because it may allow all the ones in the 16 bits. So see here, this total length may range, since like header length may range from 20 to 60 bytes. So the total length may range from 20, because minimum should be at least having the header. It may range from 20 to 65535 bytes, right? So this is what the total length will be containing. Now let's see the other fields. Version, header length, service type, total length, all are done. Now this row is completely dedicated to the fragmentation. So we will talk about fragmentation later. So here I am not going to explain this row because this row is completely dedicated to the fragmentation, and this row will be explicitly explained when I am explaining the fragmentation. Okay. Now let's go to this time to live field. Time to live field is saying 8 bits. So what is this TTL or time to live? It is saying that if you are forwarding some packet to some router or some intermediate device, then that packet basically decrements the counter of TTL. So suppose you are forwarding some packet with 15 as a TTL, then this, let's suppose this is the router, then this router will decrement it and then it will send the packet with the TTL value equal to 14. And then what it will do? It will also send the packet with the TTL value with equal to 13. So if you see here the packet is having TTL value as 13, and then once the packet leaves this router, it will also decrement its value, and then TTL value will decrement it to 12. Like that it will keep on doing. So what is the benefit of doing it? Once it gets 0, TTL tells us time to live, or how many hops that we can have in between. So once it gets to 0, let's suppose this router is having the TTL, like this router is receiving the TTL value to 1. Then once it forwards, the TTL value will become 0, right? Because it has received TTL value to 1. Now once it forwards, the TTL value will become 0. And now to this router, once the TTL value is 0, like once the receiving packet is having TTL value as 0, then it will completely discard this packet. Which means what? This router is basically not allowing this packet to go further. Why? Because it is exceeding our expectation of number of hops. So we were not expecting of number of hops to be 15 between this source and let's suppose this is the destination, between this destination. So what it is doing, like it is exceeding our number of hops, which means like this packet is misrouted, something bad has happened and this packet has been misrouted. So maybe it may go into the loop, which means if from this router to this router to this router and then to this router and then maybe to this router and then maybe to this router. So this is a TTL which prevents the loop, and which also prevents like if something some bad or misrouting has happened, then it will prevent it, which means the packet does not live over the internet forever. After some number of hops, it automatically get discarded. So that's why this field is very important, this TTL field. Now suppose that you have received, this router has received with the TTL value 1. Now it will forward the packet with TTL value 0, right? Now this is destination. This is destination. So what do you think? Destination has received a packet with the TTL value 0. So what do you think? Should destination discard it or should destination accept it? So obviously destination should accept it, right? Because at this point there is no point of discarding. So that's why destination accept it. But suppose instead of this is not a destination, this is a router itself. This is some router, some intermediate router, right? Some intermediate router. And it has received with the TTL value 0. Then what will this intermediate router will do? It will completely discard the packet. Why? Because it need to decrement the TTL value, and once it decrement, it will become negative, and TTL cannot be negative. So it will discard the packet. So that's the difference. If the destination is getting the TTL value 0, then it will accept the packet. But if the intermediate router is getting TTL value 0, then it will discard the packet. Right? So that's where we use TTL value. Now next field is protocol. So this protocol basically is used to tell what is the higher level protocols that we are using, which means that whenever you are using this IP header, this is IP header. Now IP can encapsulate any of the packet. So which means it could be consisting the TCP header, right, inside the IP data. So this is completely the IP data. See here, where is that picture? Yeah. So this is see here, this completely is IP data. Inside that you may be having TCP, right? TCP header. Inside that you may be having TCP header. So this protocol field, like this field, protocol field, is telling us that which higher level protocol header you are encapsulating. Suppose this is TCP. Then this protocol, I do not remember exact numbers, I think this is 16 or 17, then this protocol field will be having 16. Suppose this is UDP, then this protocol field will be having 17, something like that. So don't go with these numbers, I'm just giving an example. And there are some protocols called ICMP, ICGP or something like that. Then in that case, like this is having some value, let's suppose 2 or 3, something like that, okay? Something 3. So don't go with these numbers, but yeah, this protocol field tells us that which high level protocol we are using, which means this IP is encapsulating which header, right? That's where we are using this protocol field. Now there is another field which is header checksum. Header checksum is used, like as the name says, it is used to detect the errors in the header. So IP is unreliable protocol, which means that IP do not care about the errors in data, which means if you are sending data, then if data is corrupted, IP does not care about it, but IP cares about the checksum in the header or the error in the header. Why? Because suppose some mistake is there, maybe the total length got corrupted and maybe the header length got corrupted, maybe TTL got corrupted, TTL got 0 or negative, something like that. So maybe like this, these are two important fields, maybe source IP got corrupted, destination IP got corrupted. So these are very important fields, right, as per the IP. Because if source IP or destination IP get corrupted, then the whole communication will be misleaded, or any of the field. Like when we will studying the fragmentation, then you will got to know, then if these of the fields get corrupted, then also there is a major problem. So header is containing very important information, so that's why IP provides the header checksum. So how we calculate this header checksum is like that. Suppose this is your IP packet, which is having some value, maybe version 4, maybe this is 5, which means I think header length, which means header length is 20. This 0 is I think type of service. This 28 was total length. So let's suppose the total length is 28 or something like that, right? So basically these are the fields in the IP. This is the source IP, this is the destination IP, like that. Then what we do, since the checksum is basically having 16 bits, that's why we divide it into the pair of 16, which means we take this 16 bits, we take these 16 bits, we take these 16 bits, then these 16 bits, like that. So we have divided in the 16, 16, 16, 16, like that, right? And we write it in the binary or hexadecimal, whatever format you like, and then we sum it up. Now this one, like then once we sum it up, whatever carry we are getting, we again add the carry, and this is called wrapped sum. So we add this carry 1 to E, which now it has become 344F, and then what we do, we complement it, which means, like if you remember the 2's complement or 1's complement in the binary system, then from 0 to 1 we do, right? And to complement here, we just subtract it from F minus 344F. So if you like if you do it individual bits, so F minus 3 will be C, F minus 4 will be B, F minus 4 will be again B, F minus F will be 0. So that's how we complement it, and then that's how we are getting the checksum, and then we put the checksum back to this field, right? So that's how we calculate the checksum. Now if some of the bit, like any of the field get corrupted, let's suppose this field get corrupted, which is the source IP, let's suppose this 10.12 is source IP, then let's suppose this get corrupted, then this sum and then finally the checksum will not be matching with the checksum value, right? Suppose some intermediate router calculates the checksum, then this will not be matching my checksum value, and then the intermediate router will discard the packet because the checksum value is not matching with the expected value. So that's how checksum is helpful. Now suppose TTL, like there is some intermediate router which change the TTL. So if you remember, TTL is third row first 8 bits, right? So suppose some intermediate router is there and this change the TTL, and that is supposed to change the TTL itself, right? So the intermediate router will make is 3. So that's why, like, there are some fields that intermediate routers change. That's why every router calculate the checksum and put the checksum again, because since they are changing this field, at least this to 3, then they have to calculate the checksum again and then put the checksum again in the checksum field. So checksum is getting calculated at every router because they are changing the fields, right? So let me write it here. Checksum gets calculated at every router, right? Now, yeah, this is all about the header checksum. This row we will be studying later because this row is completely dedicated to the fragmentation. So we will be studying this later. And now we have source IP and destination IP, which are obvious. Like source IP just tells us the IP address of the source host, and destination IP tells us the IP address of the destination host. Now last field is options, and options is also like we will not use it, so we will not be studying it. So a datagram header can have up to the 40 bytes of option, and option can be used for the network testing and debugging. So this is not what we are going to study, and like these details are also not given in the textbooks because this is not relevant to us as a I mean, this is relevant only when we are very much specific into IT and networking administration or these kind of jobs, but not in the general study. So we will not be studying this option field, and that completes our IP header apart from this row. So fields are very easy, like from the name itself, like everything is obvious. So, and we have not studied this row, we will study it once we study the fragmentation, right? Now let's move to some of the questions. Let's solve this question. So this question is saying that IP before has arrived with the first 8 bits as this. The receiver discards the packet. Why? So they are giving us the first 8 bits in the binary. This 2 means the like underlying or the enclosed number is in the binary form. So receiver is discarding this packet. What do you think? Like what went wrong? So if you see the first 4 bits, these are telling our IP version. So what is this version? If you check the first 4 bits, then you will be saying that this is a version 4, right? So there is no problem in this. So version 4, and there is no problem in this. Now what does this tell? This tells us that my header length, so if you remember the next four fields are header length, this tells us the header length is 2, right? Header length is 2, which means actual header length should be 2 into 4 because it has always a scale with the 4, so which means this is 8. So can the actual header length be 8? No, right? Actual header length has to be 20 at least, so it cannot be 8. That's why it is discarding the packet, right? Because of the next four fields. Now let's solve next question. In IPv4 packet, the header length value is this. Okay, so they have given the header length value to be this, which means 2 power 0, 2 power 1, 2 power 3, 2 power 4, 0, 1, 2, 3. So this is basically 8, and actual header length should be the 32 bytes. And then what they are asking, how many bytes of options are being carried? So out of those 32 bytes, 20 bytes are for like without options, and then we have the options after 20 bytes. So what do you think? This is 20 and the total is 32, which means 12 bytes are for options, right? 12 bytes are for options. So I hope that is okay. Now let's move to the next question. In this question they are saying, in an IPv4 packet the value of header length is 5, okay, which means the actual header length should be 20, and the value of total length field is 28, which in the hexadecimal, okay, which means if you convert this into decimal, then it will be 16 into 2 plus 16 power 0 into 8, which means 8, then this is 40 basically. So the total length is 40 and the header length is 20, which means this is 20 bytes of header they are containing, and then after that I have the data. This is the data, not the options. Okay, how many bytes of the data? Okay, they are asking the how many bytes of the data, which is very easy, just 20 bytes. And if they ask how many bytes of options that we are having, then 0 bytes of options. So options, because the header length is 20 bytes, so there is no scope of options, so options of 0 bytes, data of 20 bytes, right? Now let's solve the next question. In an IPv4 packet, like IPv4 packet has arrived, the first few hexadecimal digits are shown like this. How many hops can this packet travel before being dropped? So basically they are asking about the TTL field. The data belong to the to what upper layer protocol, and they are asking also about like which protocol number is there. So suppose like we do not know the mapping, if the protocol number is 17, then suppose we do not know, so let's not worry about it. Let's just find out the protocol number and also find out the TTL value. So this is, I think, first 4 bits, first 8 bits. Now let me just go to the IP header and let me just paste the IP header here itself so that we can quickly solve this question. This is the IP header, and let me just copy this IP header. So if you see, the header length is 5, which means header length is 5 means like total header length should be header length is 5 into 4, which is 20 bytes, which means this is 4 bytes, sorry, this is 1 byte, 2 byte, 3 bytes, 4 bytes, 5 bytes, 6, 7, 8, 9, 10. They have only given some 10 bytes. They have not given the total header value. That is okay because they are only asking about the TTL. So the TTL is basically present after how many bytes? TTL, see, these are the 4 bytes, right? Like these are the 4 bytes because 32 bits. These are the 4 bytes. 4 bytes. So after 8 bytes, TTL is there. So this is 1 byte, 2 byte, 3 byte, 4, 5, 6, 7, 8. So TTL is 1 only, right? I mean TTL is 0, 1. 0, 1 in the hexadecimal will be 1 only, right? So TTL value is just 1, which means the packet can travel only one hop. So the receiving router is having the TTL value as 1, which means now the TTL value will become 0. And the packet can travel till this point only. It cannot go off after it, which means if this is the destination, then I'm done. I mean, that is a good news. If this is not a destination, then the packet will get discarded. Now they are asking about the protocol field also. Protocol field is basically 02 because this is after TTL and this is 02, and 02 in the hexadecimal, and the binary like the decimal should be 2 only. So 2 is for, I think, IGMP protocol, and this is what you do not need to remember, but I'm just telling you. So IGMP is one of the protocol that we will be studying. So 2 is for IGMP protocol, and they are asking about the what data belongs to what upper layer protocol. So this is for IGMP protocol only, right? So that's how we can solve this question. Now we will be studying about the fragmentation in the next video.